Welcome. In this presentation, I'll be talking about how you interpret the SPSS output for the paired samples t-test, and then how you'll go about writing it up APA style. The paired samples t-test is used to detect a difference between the means of two dependent variables. To give you an idea what's meant by that, consider the following research hypothesis. Let's say that the researcher believes that college students generally spend more time watching movies than reading books. We can compare the number of hours spent watching movies with the number of hours spent reading books. An important component for the paired samples t-test is that you have only one group of people that you'll be working with. And for that one group of people, you'll be measuring number of hours spent watching movies and number of hours spent reading books. Looking at the small little data square at the bottom middle, you can see that there's data shown for, well, at least 4 participants. For participants 1 through 4, it's clearly shown. And for each participant, for example, participant number 2, we can see that that person spent 4.5 hours watching movies and 1.6 hours reading books. So for each participant, we're going to get 2 measurements. The way that the paired samples t-test works is it calculates the difference between the measurements for each person. So for person 2, we said that that person watches 4.5 hours of movies and 1.6 hours is spent reading books. The difference between movie watching and book reading is 2.9 hours. For person number 1, who spends 3.1 hours watching movies and reads for 2.6 hours, the difference is 0.5. For every single person, we can calculate a difference score to find out what is the difference in the amount of time that they spend watching movies versus reading books. When calculating the difference score, it's important to know how are you going to do the subtraction. SPSS will actually take care of this for you, but it will let you know how it did the subtraction. It's important to know that it's movies minus books. That way, if the difference score is positive, you know the person spent more time watching movies. And if the difference score is negative, you know the person spent more time reading books. For our participants shown here, numbers 1 through 4, all those difference scores are positive, which means all those people spent more time watching movies than reading books. If the research hypothesis is correct, then the average difference score, that is, if we add up all the different scores and calculate their average, the average difference score for all the participants should be bigger than 0. That indicates that people are spending more time watching movies than they are reading books. On the other hand, if the null hypothesis is correct, then the average difference score for all the participants should be equal to or less than 0. Take a look at our participants 1 through 4. I changed the data so that this time, for participant number 1, that person spent 1 hour more watching a movie compared to reading a book. For participants 2 and 3, they spent the exact same amount of time watching movies and reading books. And for participant number 4, that person spent 1 more hour reading a book compared to watching movies. When we look at their difference scores, it's a difference score of 1, of 0, of 0, and of -1. The average difference score in that case would be 0. 1 plus 0 plus 0 plus a -1 divided by 4 would give you 0. Letting you know that there would be absolutely no difference, on average, between how much time people spend watching movies and reading books. So if our average difference score was 0, it would tell us, hey, no difference exists between watching movies and reading books. If the average difference score was negative, that would tell us that people are spending more time reading books than watching movies. That is, if you spend 1 hour watching a movie and 5 hours reading a book, you're going to get a -4. And if that happens for lots of people, we're going to be calculating the average of a lot of negative numbers, and so we'll get a negative difference score. When doing the paired samples t-test, there's 3 main requirements. The first requirement is that we're working with a single sample here, and that it's randomly drawn from the population, so we can then generalize back. The second requirement is that we have 2 scale measurements per person. By scale, I mean that there's equal intervals for the 2 variables that are being measured. For number 3, the distribution of those difference scores needs to be fairly normal. It doesn't have to be perfectly normal. The t-test is much more forgiving than the z-test. Z-test, as you recall, has to be perfectly normal. For t-test, whether it's single sample or paired, it just needs to be roughly normal. Well, for this scenario, we'll say that we surveyed 20 students about books and movies, and that our sample was randomly drawn from the population. We'll also say that we made 2 measurements per participant. Both of our measurements were scale variable, because with time there's equal intervals between 1 hour and 2 hours, and 2 hours and 3 hours. We made those 2 measurements per participant. On our survey, we asked each person number of hours that they spent watching movies and number of hours that they spent reading books. So each person gave us 2 measurements. Another thing that we could do is we could use SPSS to calculate the difference between amount of time people spend watching movies and amount of time that they spend reading books. We could have SPSS create a column for us of those different scores, and then actually take a look at the histogram for those different scores. I'm not going to go into how you go about doing this because people rarely do this third check of the requirement. Most people assume that the distribution is fairly normal, and the t-test is actually very robust, so it can handle a fair amount of skew. So if you have the time, you're welcome to calculate the different scores and then create the histogram. Most people just move forward past this and assume that the distribution is fairly normal. Okay, so let's come back to the null hypothesis and the research hypothesis. Null hypothesis says that the average of all those different scores is going to be, in this particular case, less than or equal to 0. It will be 0 if, on average, people spend the same amount of time reading books as they do watching movies. It's going to be less than 0 if people are spending a lot more time reading books than they are watching movies. As mentioned, if people are spending more time reading books, like 5 hours, and only spending 1 hour watching movies, movies is 1, books is 5. 1 minus 5 would give us a negative 4. If we have lots of those negative values, because people are spending more time reading books, our average difference score will also be 0. Will be less than 0. Okay, the research hypothesis in this case is that the average difference score will be greater than 0. Why? Because we think people are going to spend more time watching movies than they will reading books. And since we're calculating the difference score as movies minus books, if more time is spent watching movies and less time is spent reading books, we're going to have a big number minus a small number, and we should get lots of positive difference scores. So research hypothesis, as mentioned, is that people spend more time watching movies than reading books, leading us to expect, in this case, a difference score greater than 0. Well, here's our SPSS output. We don't actually have to focus on the whole thing. We can focus on just a few specifics. Take a look at that top left, where it's giving you the average amount of time spent with watching movies and reading books. That's going to be important. Our hypothesis was that people would spend more time watching movies than reading books. And the data is consistent with that. People spent on average 4.46 hours watching movies and 1.91 hours reading books. So that's good. So anytime you're going to look at your data, you want to check those two means and say, did they go the way I expected? We expected more time to be spent watching movies and reading books, and the data is supporting that. That's the first and very important check to make. Then, again, looking at the whole SPS output, focus your attention on the bottom right. And the bottom right is going to give you 3 other very important pieces of information. The t-statistic, which is 2.939, the degrees of freedom, which is 19 degrees of freedom, and the significance for a two-tailed test, in this case it's 0.008. And that significance, that's telling you the probability that this result could be due entirely because of sampling error. Okay, so as mentioned, once you check the two means, making sure that they're the correct relationship, that the mean you expect to be bigger was actually bigger, then you want to find out, well, is that difference that you hope for, is it statistically significant? Is it truly something that is not likely to be the result of sampling error? We can reject the null hypothesis and the idea that our results are due to sampling error if the probability of the outcome is less than or equal to 0.05. Well, looking at the significance two-tail, it says that the probability is 0.008. That's less than it happening due to chance 1 out of every 100 times. Probability is less than 1%. That's pretty good. We want a probability less than our alpha level of 0.05. Now, one thing to point out is that our research hypothesis, as you probably already were aware of, is not a two-tailed test. If it had been a two-tailed test, we would have said, I believe there is a difference between how much time people spend watching movies and how much time they spend reading books. And you would have just left it like that there was just a difference. But we actually specified a particular direction. We said people spend more time watching movies compared to reading books. So we actually had a one-tailed hypothesis. Well, SPSS doesn't give you the probability for one-tailed. It only does it for two-tailed. It leaves it up to you to figure out what the probability is for a one-tailed. Fortunately, that's pretty easy to do. If you're doing a one-tailed test, you take that significance two-tailed value, in this case the 0.008, and you divide it in half. And that will give you the probability for it being a one-tailed test. Why is that? Well, take a look at our distribution here. SPSS is giving us a probability. If it were a two-tailed test, the probability is 0.008. Looking at our distribution, that means there's 0.004 on the bottom left and 0.004 at the top right. So SPSS says, well, the probability that your sample mean of difference scores is as far away as it is from the expected difference, average difference score of 0. It's pretty small. The t was 2.939. That's 2.939 standard errors away from an average difference score of 0. We were expecting a positive t-value because we were expecting people to spend more time watching movies than reading books. And so instead of it being two-tailed, it was just going to be one-tailed. And so we're left with that 0.004. So whenever you're doing a one-tailed test, you take the significance two-tailed and you simply divide it in half. And that is a probability that you will get a t-value as big as 2.939 or greater. Well, do we reject the null hypothesis or do we retain it? If the probability is less than 0.05, we get to reject it. And in this case, our probability is 0.004, which is certainly less than our alpha level of 0.05. So yes, we're going to be able to reject the null hypothesis. The other pieces of information are going to need to go into the report. So we would say, college students spend more time watching movies than reading. T, and it's italicized since it's a statistic, and then in parentheses 19, that's our degrees of freedom, the DF, is equal to 2.939. That's how many standard errors our sample mean of different scores was from the expected value of 0, no difference, and probability less than or equal to 0.05. So again, the 19 is our degrees of freedom, the 2.939 is the t-value, and then we report whether the probability was less than or equal to 0.05, allowing us to reject the null, or we would report p greater than 0.05 if we needed to retain the null. Now I actually did the analysis on watching videos as well as reading books, and those two different distributions were both normally distributed. So if I want to let my reader know the averages for both watching videos and reading books, I'd report the mean and standard deviation. So here's how we would do the APA style write-up of our results, providing a reader with all the information. A one-tailed paired samples t-test revealed that college students spend more hours watching videos, italicized M equals 4.46, italicized S equals 2.59, compared to reading books, italicized M equals 1.91, italicized S equals 1.46. Comma, and then our italicized T, 19 degrees of freedom, is equal to 2.939, comma, probability less than 0.05. And that's how we would write up our results based upon the SPSS output. So hopefully this overview has helped you with how you would interpret the SPSS output and how you would then write up results APA style.